Hey guys, in this video we're going to try to solve the steady state of this OLG problem, and this is our law of accumulation of physical capital. And so when we had a continuous time model, we did this as a differential and we had a k dot that was going to be equal to 0. And here we don't have a dot, we just have an aggregate number. So the equivalent statement to k dot equals 0 in discrete time is that k t plus 1 is equal to kt, which is equal to some k bar, where physical capital per capita remains the same for all time. So what we're going to do, our strategy for trying to solve this, will be to replace all the k's, so this one and this one, with a single k bar, and then we're going to try to dig out the k and solve the equation. So let's go. Get rid of some of this. Okay. We will have that k bar is equal to, I'm going to begin by multiplying this all together. We're going to build like a big ugly parameter in the end. So we're just multiplying this into here. That's going to be equal to p times the quantity 1 minus alpha a k alpha plus 1 minus p times m. Okay, let's distribute this thing across. I'm just going to give, well, let's distribute this first. So k bar, whoops, this is k bar as well, so we can combine these now. K bar is going to be equal to, here we're going to have the p and the p cancel, so the first one will be 1 minus alpha, or sorry, 1 minus a over 1 plus n, and then we'll add to that on top the 1 minus alpha, and then that'll be times a k alpha, and then plus 1 minus a, 1 minus p, m, divided by p 1 plus n. So we're getting closer, sort of, and maybe you can already see what the problem is. The problem is that we do not have a nice way to separate out that k. So just to make things clearer, let's actually put this a up here, and then let's just define some new variables. We're just gonna, to make things easier to see, all this junk, let's just call it gamma, and all this junk, let's just call it epsilon. So our equation right now is that k bar is equal to gamma k alpha, k bar alpha, plus epsilon. So to find a single unique value for k bar, it's not really possible. We could subtract k bar minus gamma k alpha, and then we could factor, but we can't factor away totally to get all the k's together. What we want to do, we want to have something where we have like a k bar equals, you know, gamma divided by epsilon or something, right? A single k bar that equals some single mess of parameters. But here, it doesn't look like it's going to be possible. You know, we could try to take the log of both sides to knock down this alpha, and so you could get like the natural log of k bar is equal to alpha natural log of all of this. Actually, we can't even do that because you can't do anything with addition inside of the natural log. We can't split up this addition part because this is not a linear function. It doesn't distribute across a plus. So that's out of the question. So yeah, what I was told is that the class last year during the test was told that the question does not have a solution. And I don't know if that's true. I think that there's another way to investigate a potential answer using the implicit value theorem. And Carlos tried it that way, but he said it didn't work, but maybe, you know, someone else can figure it out. So k bar equals, I have no idea. But the important point is that we know how to get to this point, that we substituted all k's equal k bar, and then we try to rearrange the problem to find a single k bar equals some combination of a's and alphas and n's and m's. That would be the dream. But for now, the dream is dead. So let me know if you have a better answer than that. Sorry, guys.